Hello, I'm going to go through that last tutorial number 11 on thin film interference, and I will share my screen. Okay, so we have a little bit of a review here from Physics 105. You remember that back then we talked about what a pulse did when it went from one medium to another, and we were using springs, and we had two springs, one fast and one slow, that were connected together. And the the characteristic of the springs that determined the speed of pulses on those springs was the mass density. And we're told in this case that we're considering that we've got a huge mass density on the right and a smaller mass density on the left. And you remember that the speed of pulses on a spring or string depended on the tension in the spring or string divided by that mass density. And because of Newton's third law, the left spring is pulling on the right spring just as hard as the right spring is pulling back on the left spring. And so the tension is going to be the same for both. And so whichever of those springs has the bigger mass density is going to be the slow uh, spring. And so this side over here is slow, and this over here is the fast. Now, what we found was that when a pulse came in from fast to slow or from light to heavy, this boundary was like a fixed end, like it was tied to a wall. And so when the pulse bounced back, it bounced back inverted. Okay, and so it came in on top and came back on the bottom. Now, when this incident pulse hit the boundary, it split, part of it going into the new medium, the slow spring, and part of it bouncing back into the original spring. Well, we found that the transmitted pulse, the one that goes on, never gets flipped, never gets flipped. But it does slow down, and the front of the pulse slows before the back of the pulse. And so when this pulse gets over into the slow spring, it's narrower. And also, since both of these pulses, I call them the twins, since both of them were born at the same time at the same hospital, right here, and then scurried away from each other, um, the fast pulse got further away from the hospital than the slow pulse. And so that's what the pulses would look like shortly after the original pulse hit the boundary and split. Now, on the other hand, if we have a pulse come in from the slow side to the fast side, when it hits the boundary acts like a free end. And we know that in that case, the pulse comes back on the same side. And again, the the transmitted pulse never gets flipped, but it does speed up. Okay, and so this pulse would be further away from their birthplace. These are the twins, um, and it would be wider than the original. Okay, and so that's what we learned in Physics 105. Um, so we drew the pulses, and um, if you've got friends in the room while you're watching this, talk to them about it and see if they still remember all of that. Now, we're going to talk about thin film interference. We talked a little bit about this in a lecture on Thursday. You may have observed that when a beam of light strikes a piece of glass, it is partially reflected back and partially transmitted into the glass, similar to the behavior of a pulse on a spring when it reaches the junction between two connected springs. In this tutorial, we consider a beam of light in air, where the light travels fast, incident on a soap film, where the light travels slower. Okay? We make an analogy between this situation and a pulse incident on a boundary between two springs of different mass densities. In this analogy, would the soap film better correspond to the spring with a larger linear mass density or with a smaller linear density? The soap corresponds to the larger mu, okay, because light is slower in the soap. Okay. Now, when comparing two materials of different indices of refraction, the material with the higher index of refraction is sometimes said to be more optically dense than the other. Is this terminology consistent with the analogy that you made in part A? Yes. Okay. Uh, we were talking about mass density with the case of the spring. In this case, optically dense represents, uh, you know, how much the medium slows down the light. So we're going to send some light um, into a soap film. And so here's my film, and we've got air coming in at some angle there, and it's being held up by a loop like what we saw in class, but we're not showing the loop here. Only a small portion of the film has been shown, and the thickness of the film is greatly exaggerated. In answering the following questions, use an analogy between this situation and the connected springs in part A and part B. So let's look at the first boundary here. In the diagram, draw rays that correspond to the light that is transmitted and reflected at the first boundary here on the left. Okay. Now I know that the, I think everyone should just go and get themselves a ruler right now. Okay, I'm back. So we know that the reflected wave is going to come off at the same angle that it went in at relative to a normal. I'm going to try my best to draw this correctly. Uh, okay. And then we're going to bend the light towards the normal. So it would go something like this. And so some of the energy would bounce back. That's the reflected ray. And some of it would go into the slower medium there. And because we're going from fast to slow, there would be an inversion at this boundary here. If a crest went in, a trough would come out. Okay. Is the frequency of the transmitted wave in the film greater than, less than, or equal to the frequency of the incident wave? Well, that is equal to. We found that in Physics 105 that if I sent a um, a wave into the water, say from a boat, trying to attract my friend Flipper, that every time that wave uh, slapped the surface of the water, with the wave fronts, it would send another disturbance into the water. And so if the wave in the air is slapping uh, the water 5 times a second, then we're sending 5 wave fronts each second into the water. So uh, the frequency of the wave is always equal to the frequency of the disturbance causing the wave. And in this case, it's the wave in the air that's causing the wave in the soap. So um, they're equal. Is the wavelength of the transmitted wave in the film greater than, less than, or equal to the wavelength of the incident wave? Well, it's going to be less than. Okay. Remember, the wave equation was that the speed of the wave was equal to the frequency of the wave times the wavelength. Well, if if the speed becomes smaller in the soap and the frequency stays the same, then the wavelength has to get smaller in the soap. Now we know that uh, the index of refraction of the soap is equal to the speed of light in air, well, vacuum actually, but also air, divided by the speed in the soap. And so that means that um, the I can say that the wavelength uh, in the soap is going to be equal to the wavelength in air divided by that index of refraction of the soap. And that's going to be the wavelength in air divided by 4/3 for the soap. For light incident on the first boundary, would the reflection at this boundary be more like the reflection from a fixed end or a free end? We are going from fast to slow. So this is going to act like, this will act like a fixed end. And there will be an inversion there. Okay. On the basis of your answers above, at the first boundary, would the reflected wave be in phase or 180 degrees, that would be half a wavelength, out of phase with the incident wave? In other words, is there a phase change upon reflection? It would be 180 degrees out of phase with the incident wave. Uh, is there an incident phase change? Yes, there is a phase change. At the first boundary, would the transmitted wave be in phase or 100 degrees out of phase with the incident wave? Is there a phase change upon transmission? Well, you remember on the first page, we talked about the fact that there is never a phase change in the transmitted wave. So it would be in phase. Uh, the transmitted wave never gets inverted. Okay. Well, that wasn't so bad. So now we're told to continue that transmitted ray from part one through the film to the second boundary on the right, and then draw rays that correspond to the light that is transmitted and reflected at the second boundary. Okay, so let's do that. So we send this one back. And then we let that, when it goes into the air, we then let that bend away from the normal. And it doesn't take much in the way of reasoning to see that if these two sides are parallel to each other, that these two rays will be parallel to each other. And so I've got a reflected wave here and a transmitted wave here. Okay. Now, for ice, for light incident on the second boundary, would the reflection at this boundary be more like a reflection from a fixed end or a free end? Okay, in this case, we're going from slow to fast. It acts like a free end. Okay. At the second boundary, would the reflected wave be in phase or 180 degrees out of phase with the incident wave in the film? Um, the so we're talking about uh, this wave in the film that is bounced off of the second surface versus this wave in the film that hit the second surface. Okay, we're talking about this reflection right here. And the answer is that it would be in phase. If it's acting like a free end, uh, a crest goes in, a crest comes out. Okay, I'll just write that down. Crest in, crest out. Now, continue the reflected ray from part two through the film and back to the first boundary. Then draw rays that correspond to the light that is transmitted and reflected at this boundary. Well, this is getting messy, isn't it? Okay, so here I'm going to have the transmitted wave come out. And again, we can argue that this one is going to come out parallel to the one that was reflected off the first surface. Okay. And so if I put my eye here, um, I'm going to see those two rays coming back at me, one that's been bounced off the first surface of the soap, and one that's gone into the soap, come back, and then come out of the soap after bouncing off the back surface of the soap. And there will be some reflection that goes back here. Again, angle in is equal to angle out. Okay. So we've done that. Would there be a phase change on transmission at this boundary? No. Okay. Never a phase change on transmission. In other words, the transmitted wave is never flipped. Okay, we're going to take light of frequency 7.5 times 10 to the 14 hertz, incident on the left side of the soap film. And first of all, we want to do some number crunching. Um, the frequency of the wave in the soap film is going to be the same as in the, that's what we said before. It's the same as in air. So that's going to be 7.5 times 10 to the 14 hertz. Remember, that doesn't change when we go from one medium to the other. Well, the wavelength in air, I can find from the wave equation, uh, where the speed is the speed of light, and that's going to be the frequency times the wavelength. So when I'm solving for the wavelength, that's going to be equal to the speed of light divided by that frequency. The speed of light is 3 times 10 to the 8th meters per second. We're told that the frequency is 7.5 times 10 to the 14 hertz. A hertz is just a per second, so the per second cancels out, and I get meters. And indeed, what I get is 4 times 10 to the minus 7 meters. Well, that's small. But we're going to put it in nanometers. And you remember, a nanometer is equal to 10 to the minus 9 meters. Okay? So this is going to be 400 nanometers. Well, now we want the wavelength in the soap, in the film. It's a soap film. And that's going to be the wavelength in air divided by uh, the index of refraction of soap. Well, that's going to be my 400 nanometers divided by 4/3, and that's going to be 300 nanometers. Okay, it almost looks like these numbers have been cooked to turn out nice and easy for us. Suppose that an observer were located on the left side of the soap film in part C. Well, that's what we were already talking about. I put my eyeball here and I watch these two rays come away from the soap towards my eye. How would these rays be different if the light were incident at essentially a normal incidence? Well, we drew it at an angle so that we could see all of the different comings and goings. And you can see that even at this angle, it got kind of messy inside the soap film. If I came in at normal incidence, everything would stay at normal incidence. Everything would just bounce back and forth and come out uh, at normal incidence. But we would still have the same um, phase shift on the first surface and no phase shift on the second reflection here. So in essence, um, no difference. Okay. We we only did it at an angle just so that we could uh, see where all the rays were going without them being on top of each other. Okay, now things are going to get interesting. We're going to let um, that picture here represent a small slice of my soap film, maybe uh, a small slice right there. And that's why it looked uh, so uniform in its width. But in truth, this soap film has been affected by gravity, and the soap has kind of drooped a little bit so that it's thicker at the bottom than it is at the top. And we're going to send that same light, the light that has frequency 7.5 times 10 to the 14 hertz, and it's going into the soap that has index of refraction 4/3, and we're going to send it in at normal incidence. And first of all, we're going to look at observer A. And where observer A is looking, the film is 75 nanometers thick. Now, the ray that goes into the soap and bounces back from the second surface back here, that ray has to go through the soap once to get to the back side, and then once again to get back to the front side. So if this is some distance t or thickness t, I'm going to get a path length difference. We'll call it delta S. Path length difference is going to be 2t. Okay. And so if I consider the two reflected rays that reach observer A, similar to the rays that you identified in part E of section 2, how much further does one of these rays travel than the other in reaching observer A uh, in millimeters? Uh, let's let's do it in nanometers. Yeah, I think that might be a um, I think that might be a typo there. Well, I know that the delta S is going to be twice the thickness, and that's going to be twice 75 nanometers or 150 nanometers. What is the phase difference between these rays? Be sure to take into account the changes that you identified in part C of section 2, as well as any phase difference due to the path length difference. Well, 150 nanometers is equal to 1/2 the wavelength in soap. Okay, remember, we found that the wavelength in soap was 300 nanometers. And I'll just write that over here. So the phase change due to the extra travel is half a wavelength. And then plus I have an inversion at the front surface, but not at the back surface. So that introduces another half wavelength. And so the total phase difference, um, the phase difference difference, I'm not sure if I spelled that correctly, is going to equal a half a wavelength uh, due to this extra travel. Um, that's due to the delta S plus 1/2 wavelength due to the inversion at the first boundary. And so that's going to equal 1 wavelength of the soap. Oh, I'm sorry, I was down below the horizon there. So my total path difference, I have a half of a wavelength due to this uh, extra path length, and I have a half wavelength due to the flippage that happened on the first surface, but not on the back surface. And so that gives me one whole wavelength. And so when this wave comes back, um, if I have a crest on one of those rays, I'm going to have a crest on the other ray. We're going to be behind by one whole wavelength, but that's still going to put crest in the same place as crest. So is an observer at A looking at a region of maximum brightness or minimum brightness? So that's going to be maximum brightness or constructive interference. And the reasoning is right here, is that if if one wave is going and the other wave is just one wavelength behind, I'm still going to have crest to crest and trough to trough and crest to crest and trough to trough. Observer B is looking at a part of the film that is 150 nanometers thick. Well, in that case, um, the delta S or path length difference is going to be twice the thickness or twice 150 nanometers, which is 300 nanometers, which is exactly the wavelength in the SOAP. So the phase difference between the two rays is going to be one wavelength due to the SOAP due to the change in path length, plus that flippage that happened on the first surface. And so that's going to be 3/2 lambda in the SOAP. And so that's going to be a region of minimum brightness, maximum darkness. Okay, so it will be dark, and this will be bright. Okay, now observer C. So we said that uh, this was going to be dark, and this would be bright. Now, observer C is looking at this region here where it is thinner than 75 nanometers. Okay. And in that area, if we go all the way to the end where we have virtually zero thickness, at that point, we don't have a path length difference. Delta S is zero, but we still have that inversion on the front surface and no inversion on the back surface. So there's still going to be a phase difference of 1/2 wavelength in the SOAP. And so this is going to be a dark region. And you remember that's what we saw in class when we had that SOAP film, was that we got the colors, we got the bright and the dark spots or stripes um, as we moved down that SOAP film. But at the top, where it got really, really thin, it was dark. And that was because of that phase shift at the first surface, but not at the second surface. Okay, so it's going to appear dark, and that's because the phase shift is going to be about zero, okay, for my delta S, or let's say that's about zero. But then I've got that 1/2 wavelength in the SOAP, due to the the flippage, due to the inversion on the first surface. Describe the appearance of the film as a whole. Well, it's going to be dark at the top, and then I'm going to have bright, and then dark, and then I'm going to have bright, and then I'm going to have dark, then I'm going to have bright. Okay. And so dark, bright, dark, bright, dark, bright, dark, bright. What are the three smallest film thicknesses for which there would be maximum constructive interference? Okay. Well, um, for maximum constructive interference, we would have the path length difference of 2t is going to equal to m plus 1/2 lambda of the SOAP for m equals 0, 1, and 2. And so if I have m equals 0, that's going to give me t is equal to the lambda of the SOAP divided by 4, and that's going to be 75 nanometers. And that's the one that we found on the previous page. When m is equal to 1, well, that's going to give me t is equal to 3/4 lambda in the SOAP, and that's going to be 225 nanometers. And for m equals 2, that's going to give me a t of 5/4 lambda of the SOAP, and that's going to give me 375 nanometers. What are the three smallest film thicknesses for which there would be maximum destructive interference? So these are the bright spots, and these would be the dark spots or bands. Okay. Well, in this case, I would have minimum when the 2t, or the path length difference, is equal to an integer number of wavelengths in the SOAP, because I already have that half wavelength due to the front surface. And this would be for m equal 1, 2, and 3. And so for m equal 1, I'm going to have t equal to a lambda SOAP over 2. And that's going to give me 150 nanometers. And that's what we saw again on the other page. For m equals 2, I'm going to have t equal to lambda SOAP, or 300 nanometers. For m equal 3, I'm going to have t equals 3/2 lambda of the SOAP. That's going to be 450 nanometers. Okay. We're told that the thickness of the film is 1650 nanometers at the bottom of the film, where the film is the thickest. Would this part appear bright, dark, or in between? Well, let's figure that out. Okay. The change in path length, whoops, sorry. The change in path length, we're calling delta S, remember, is 2 times the thickness of the film. And that's going to be 2 times 1650 nanometers. And that's going to give me 3,300 nanometers, which just happens to be 11 times the wavelength in the soap. And so if there was no flippage on the front surface, this would come out after the two reflections in phase, just in step, and it would be bright. But we do have that flippage on the first boundary, the first surface. And so that means that is going to be uh, a dark region. Okay. So the phase difference would be 11 lambda in the soap due to my path length difference, plus a half wavelength of the soap due to the inversion on the first surface. Okay. Now, what if the frequency of the incident light were increased? How, if at all, would the appearance of the thinnest part of the film change? Um, well, there's still going to be an inversion on that first surface. And so for the thinnest part where I really don't have very much path length difference, I'm still going to have that 1/2 wavelength uh, phase difference. And so the thinnest part will um, still be dark, but it won't be as wide. Okay. Um, uh, Not as big a region as before. Well, why is that? Well, to get to my first uh, bright spot, I just have to get to a thickness of 1/4 wavelength. And if I have a frequency, um, if my frequency gets bigger, then my wavelength is going to get smaller. And so I don't have to go uh, to as big a thickness to get to the first bright spot. So the dark region on top would be a smaller region. Would the number of bright and dark regions increase, decrease, or stay the same? It would have to uh, increase. Again, um, the the separation between bright spots um, is 1/2 lambda in the soap, and lambda in the soap gets smaller. Okay, so looky here, we turn that over and it's blank. We are done with this tutorial. And in doing that, we have finished all the tutorials for Physics 106. Well done, well done. I'm uh, so pleased with what we've accomplished this semester. You've worked hard and you've shown courage, and I'm proud of you. So now I'm going to end this recording